The add norm layer performs two functions. First, it adds the resulting adjustments or deltas to the initial input. This process is what's called applying the residual connection. And by add, I mean a component-wise addition. So the zeroth index of the zeroth column of our initial input gets added to the zeroth index of our zeroth column of our attention output. Now, if you had my same first thought, then you're asking, why don't we just treat the output of the attention layer as the new embedding? Well, the answer is twofold. First, it simplifies optimization. By adding the initial input, you provide a direct linear path for the gradient to flow backward through its original identity. This makes training easier for the model and forms what you could call a gradient highway for the model to track back through the encoding layers. The second reason we add the residual connection is it ensures the preservation of information. Let's look at our example and forget about the residual connection for a moment. If all we did was take the output of the attention layer as the new output, then our new direction dimension for up would have dropped to 0.39. We know that direction was originally the only dimension we had initially set to 1, with all else being set to 0. So why did this happen? Well, if we look at our attention matrix for our now and modifier head, we see that the key of up, which is what holds our high direction value, is only contributing 27% of the weighted sum of our attention output. Since up's initial embedding has zeros for everything other than direction, the only contributing factor to its attention, even for its own query, is 27%, because the weighted sum of its 0.2 need for first person, 0.3 need for singular, and 0.6 need for object make up a majority of its query. This increases the attention for the tokens that have that information, which for us is predominantly the me token. So zooming out, we can see that by just taking the attention output, the predominant identity of up is diminished to be its lowest value. Just because what up learned from its direction this time around wasn't very much, doesn't mean it should shed all of its initial understanding. By applying the residual connection, it allows us to retain its direction understanding, ensuring the delta or adjustments are applied without dwarfing its original representation. That takes us to our normalization layer. The normalization layer normalizes per row vector, centering our values around 0 with a standard deviation of 1. In order to normalize, we will need to do some quick math per row vector. We will use the Greek letter sigma to denote summation across a sequence of values. This equation will sum all values, starting with I equals 0, up until I equals h, assuming h is the last index in our row vector. To calculate the mean, you sum all values in the row vector and divide by the row vector size. To calculate the variance of our row vector, we subtract the row vector mean from each value, square the result, and sum across the row vector, similarly dividing by the row vector size. And to calculate the standard deviation, we just take the square root of our variance. So finally, to normalize each value such that the mean of our values is 0 and our standard deviation is 1, the new scalar value at each index is the old value minus the mean of the row vector divided by the standard deviation. I'll carry out the math and pause to review if needed.